So in the last session we were mainly looking at the basic principles of electrochemistry that are relevant to biosensing technologies. Now I'm going to do some case studies here. So you're going to see a lot more you're going to see some repeat as well. So that's just to make sure that I'm consolidating the examples through case studies. So this is going to be the third lecture in this whole series, and this is also going to be part of the session that we have planned for the basic principles of electrochemistry which are relevant to the technologies. And I'm here in this particular lecture I'm going to be presenting more case studies for you. Okay, suggested readings again, if you're a very avid reader, go for the Bard and Faulkner electrochemistry book. That will cover all the fundamentals, and that will also give you some good examples on the biosensing applications. The presentation I'm going to give you was something that I also presented at one of the conferences. This was basically a talk that was given at the symposium that was organized by University of North Carolina in Chapel Hill. This was given under the topic real-time continuous monitoring of metabolites, basically trying to address the whole problem of artifacts, which is basically the elephant in the room. So when you're doing electrochemical measurements using variable sensing technologies, you will come across a lot of artifacts, and I'm going to be showing you lots and lots of examples of those artifacts when you look at the data here. The outline of this lecture, the last lecture that we have for the day, is mainly, again, we're going to revisit this whole idea of skin-based wearable devices, looking again at the microanatomy of skin. As I said, my area is subdermal devices, so I'll stick mainly to subdermal devices. I'm not going to talk about epidermal devices. We're going to talk about skin interstitial fluid again, just to again consolidate on the facts that we've discussed this morning, and then look at subdermal wearable devices and then give you examples. I think we've had some questions on polyphenols, so we're going to be looking at the electropolymerized phenol film and trap devices. We're going to be looking at hydrogel trap and trap devices, and then come up with some conclusions. Let's start again with wearable devices. This picture here is the classic example I gave you this morning. Anybody remembers this? This is your Google contact lens, which unfortunately has not gone that far. As you can see, this is made up of three different parts. You've got the upper lens, you've got the sensor part, which is, you can see, is in the form of this gold metallized part, and then you have the actual contact lens. And the idea was that you would use these to measure in your tear fluids. This has not gone anywhere. There's still some more work going on. I mean, I thought it would be a good example to look at other examples of sensors, wearable sensors. This is an example of tears, where you have tear as a sample matrix. You also have saliva, which could also be used as a good sample matrix. For that, you have these gum shields, gum guards. People who play rugby or contact sports, they normally wear gum shields. Even people who play hockey, they wear gum shields. You can have sensors which have been incorporated in them, and that can be used for monitoring glucose, lactate, and even cortisol and other stress hormones in the saliva. And then we already saw examples of sweat, which we discussed as epidermal sensors, and the skin interstitial fluid, which falls in the category for the biological mattress for subdermal sensors. All right, let's revisit the anatomy of the skin one more time. The top layer of the skin, as we all know, is called the epidermis. It's a thin layer. The main layer of part of that particular thin layer, which is basically sitting here, is your stratum corneum layer. The stratum corneum layer is basically the dead cell layer, and this is the layer that basically acts as a barrier, preventing any water molecules or making your skin more prone to get water going through. And then you have your subvascular plexus. These are your subvascular plexus, which are basically your fine capillaries, which are in constant equilibration with the cells that sit here in your skin compartment. Below the epidermis is the dermis, and below the subvascular plexus is your subcutaneous tissue. So when you give an injection, that goes under the fat layer. That's a hypodermic needle. Again, we'll have a slide to show you that. And then you also have your dermis here, and then you have your sweat glands, and you have other glands as well, which release the hormones as well. And then you have your subvascular plexus, which is, as I said, in constant equilibration with your skin interstitial fluid. Again, how do we access skin interstitial fluid. I think I've already shown you this slide in the morning. For those of you who were not there in the morning, this is for the benefit of them. There are different ways in which you can access the skin interstitial fluid. The advantage of skin interstitial fluid is you have a lot of volume of the skin interstitial fluid. If you have 5 liters of blood, you have 12.5 liters of skin interstitial fluid. The skin is the largest organ. You can access the skin interstitial fluid because it's a treasure trove of biomarkers, and there are different ways of doing it. You can either do microdialysis, you can do suction blisters, or you can do your microneedles. And then this is this image, SCM image of microneedles that were either made by myself or by my students there to show you that microneedles can be made out of different materials. This is a classic example wherein you've used silicon to make microneedles of different sizes. This one is an example where microneedles have been made using a technique called as photolithography. And we were able to only make one 6-inch wafer, which was giving us 8 times 8, 64 microneedles, making it really hard for us to be able to do any substantial amount of work, because you were spending more time making these needles in the lab than actually functionalizing them and using them for applications, right? And as people working in the area of biosensing, looking for clinical applications, what we need is a high throughput scalable technology which allows you to make many of those, and that's where injection molding, which shows these nice regular structures, because that's another thing that you need from your manufacturing technologies. Be able to scale it and to have uniformity, to have consistent structures, because if when we talk about electrochemical sensors, the signal that you get from your electrochemical sensors is directly proportional to the surface area. So if you have different microneedle arrays of different dimensions, you will be getting different signal values, and you wouldn't be able to make sense of those unless you knew exactly what you did a back calculation there. So it's very important that you have uniform structures, uniform geometry, uniform surface areas. And some of these studies will be about how we were able to achieve those problems. All right, I'll start off with the first clinical study that was started in 2013, which we managed to publish in this nice journal as a cover page in Analytical Methods. This is a nice picture that shows on your right hand side. This is a nice picture. You see polycarbonate as a transparent material. I mentioned to you about polycarbonate, very, very cost effective. 10 pence of polycarbonate, injection molded to give you thousands of these structures. I mean, that was a fantastic scenario for us, because we didn't want to spend too much energy and time and resources on making these devices. We wanted to focus more on functionalizing them into biosensors and using them for biosensing applications, because we had an NIHR project. So these were initially, by the end of the project we could start making them out of polycarbonate, but before that we were making these devices that we started introducing as part of our first phase were mainly made up of epoxy SU8 microneedles. They were more molded microneedles, wherein we used electric discharge milling. I showed you the picture here. This is aluminum blocks which were basically electric discharge milling to get these pyramid structures. And then how many of you have used SU8? One. SU8 is an elastomer, right? You mix the monomer and then you get a polymer. It's a very moldable substance. So you take a block, so you imagine you have your solid block where you have your microneedles, and then you pour SU8 on top of this, and then you let it set, and when you peel it off you get your SU8, which will have the inverse structures, and onto this you can pour your SU8, which is basically a polymer again, which a monomer mix again, which can be polymerized by just shining light onto it. And then you get, when you cut this off, you get your epoxy SU8 microneedles, which have got the microneedle structures that you've been looking for. Simple case of molding and casting, right? You have a mold, you make a mold with electric discharge milling, and then you pour the elastomer to the SU8 elastomer to get your mold, and then onto the mold you pour in your SU8 monomer mix, polymerize it, and then you get these nice solid structures, and they are mechanically very stable. You have to do some mechanical properties. So those of you who are looking into going into this, any platform that you develop, you need to make sure that it has the required mechanical properties. It penetrates with minimum force. You don't need a hammer to be able to insert it into the skin. You should have something which can go in with moderate thumb pressure, right? And then later on you can develop an applicator for standardization of insertion, because that's a very important thing. Because if I gave you the microneedles, everybody will be using different forces. Some of you would be very gentle to yourselves, some of them might use a little bit more force. We need a standard force there, which I mentioned is 10 newtons at a speed of 10 millimeters per second. So you can use a spring loaded applicator there to design the applicator. All right, so this was the first clinical studies that were done, and this is the device, which is an SU8 device, which is inserted on the arm, and then again you need some reference here, right? How do you know? As I said, when you do the measurements, what are you measuring? Pardon? Current you're measuring, because it's chronoamperometry, you're measuring current, you're not measuring glucose. You have to correlate this glucose to the glucose, you have to correlate this current to the glucose values. So that's what we need to do. So for that you need to have a gold standard here. So we were using a venous blood glucose monitoring system, which so we had an insulin. We had a cannula which was inserted in the forearm, and you could measure, you could draw blood every 30 minutes, every 1 hour, and you could get some point measurements, and then you could use that as your reference there. That helps you in two ways. When you do the tolerability studies, it's a visual assessment method, right? So when it's a visual assessment method, you can take the microneedles and you can ask the person, or you have been inserted with an IV cannula has been implanted into you, and we are inserting these devices. Can you compare them? And then you can get a score. So if you look here, for microneedles, the score was 10. For the cannula, the median score was around 20 and above. In the second phase, the microneedles, the median score was around again 10, and here the cannula score was again. So this also depends on the clinician who is inserting the cannula as well. But if you look at the third phase here, the microneedle score and the cannula scores are very, very close. Can anybody tell me the reason for that? I'll give you some more information here. Phase 1 and phase 2 were done in healthy volunteers. Phase 3 was done in volunteers who were type 1 diabetics. So type 1 diabetics are much more used to needles, so they don't feel the pricking as much as a healthy volunteer would feel. Therefore, the differences between the visual assessment scores for the microneedle and for the devices and for the IV cannula devices is much higher in healthy volunteers, and in phase 3 where we had type 1 diabetics, the scores are very, very similar. Yeah, so that's the case. And then we also had a look at this inflammation thing. How long does the inflammation, how long do the marks stay, and how long do the marks disappear? I've had a few. So we normally have events where we display the technology, and I think one of the questions, many times I've had people coming to the booth and asking me the simple question, how long do the marks stay for? That's a concern, right? And it's a genuine concern, especially if the marks are on parts of the body that are exposed, right? Forearm, I mean, a lot of people, when you're wearing half sleeve shirts, easily exposed. So you want the marks to disappear as soon as possible. I'll show you further studies where we further subdivided how the marks can look like. So this was some studies that was done and then published in Analytical Methods here. And then I'm going to give you another example. I think I already alluded to this example, wherein we use the same microneedle biosensors for monitoring penicillin. I gave you the example of therapeutic drug monitoring. I gave you the example of antimicrobial resistance. I showed you how there's a need for a technology that allows you to monitor the pharmacodynamics and pharmacokinetics of drugs and how they are metabolized in your body, so that you can be offered personalized treatments. So this is an example here, and this paper I can proudly state that was published in Lancet, which is a high impact factor journal, Lancet Digital Health, and this was again work done by Timothy Rawson here, and this is where you can see the result data here expressed in the form of what we call as a bland Altman plot. This is the line which means that there is no difference between the reference measured sample, using the gold standard and your sensor here. And the further you move away from the line, the poor is the performance. But in our case, you have these two lines which are the confidence limits of 95%, and the data points were mostly scattered within these two confidence level of 95% there. So which is good result for us as an initial start. And here you can see we have gold coated ones, because gold coated microneedle arrays seem to be much more compatible with penicillin oxidase, and the bioreceptor here was penicillin oxidase here. And now I move to the next case study that we did. This is basically simultaneous monitoring in ambulatory conditions. No points for guessing who the participant here is, although the face has been blacked off. This is basically monitoring glucose and lactate simultaneously in the lab and on a treadmill and things like that. Now what happens is, before you start a study, right, so you will see this happening a lot. Once you all, NIT Rourkela has this practice of going into translational research, and you get projects wherein you're meant to be monitoring simultaneous monitoring of glucose and lactate, you will be seeing Professor Prasun and Professor Khalid running around in the shorts with sensors stuck all around them, because the rule is you cannot use these sensors in volunteers until unless you have full approvals from the research ethics approvals. But you cannot waste that time, because that's a 6 months duration. So the best thing you can do is you can apply these, the investigators, the principal investigators and the co-investigators, they normally apply this on themselves. So good luck to Professor Khalid and Professor Prasun to try these sensors on themselves. I did my part. I did my, as I said, I used to always joke with my students that my body is for science, and I think my students made full use of it, and they stuck sensors over me for measuring glucose and lactate. So in this particular case, I've got a glucose sensor, and this is me with the tablet there, which is showing a profile of my glucose values. This is me in the lab. As you can see in the background, you can see the 3D printers there, and this is me in the A-STEM lab, which is we had a sports and exercise lab in Swansea University, and I have the sensors which have been stuck. Again, this is on the, you can see this pink band there, which is holding the sensor in place, and me running on a treadmill there. It's not a bad thing to do, to be honest. In fact, it tells you a lot about your own body, and it's good to have all this information, especially if you want to have a good health, and if you're somebody who is a fitness fanatic as well. So these are some results here on your screen, just to show you how these look like, so that you can this can gear you up towards translational studies that you want to do. This is basically the device. It looks like it's a polycarbonate device which looks a bit silvery in color. It's got 4 islands. The working electrodes are made up of platinum. The counter electrodes are made up of platinum as well, and you have a reference electrode which is silver, which we modify into a silver chloride using a solution of ferric chloride, or we also use bleach to convert the silver into silver chloride. This is basically a PCB, because when we did the first experiments, I think I hated it, because I was the person who used to stay overnight for the 24-hour studies. And can you imagine these devices looking like spiders with wires coming out, and then the wires connected with a crocodile clip? I hated that, because I was woken up, I would be sitting on the chair, and suddenly I would wake up and I'd see one of the connections had come off, which meant that you would start again. And that's a real pain in the backside. So the next thing you want to do is you really want more stable connectors here, and that's why we have this PCB connectors here, so that you have stable connections, proper mini USB type of connectors, which can then make sure that, and you can see this goes into that side, and then you have your wires nicely color coded, so that nothing, and even that one goes in and it's nicely secured. You have to make sure your connections are really well secured here. And then you have this portable potentiostat here. I mean, never trust commercially available portable potentiostats. I would trust a portable potentiostat that was developed by Khalid's research group at Imperial College more than I would trust portable potential. The only problem I have is when you're doing clinical studies, they ask for potentiostats which are CE marked. I have no idea what is the basis for the CE marking, but honestly, the portable potentiostats were not the best. So if you have facilities, or if you have collaborations within NIT where you have electrical engineers, electronic engineers who can make these potentiostats, I think Khalid has already made some of these in his past tenure. Go for that. You can make multi-channel, much more reliable potentiostats there. We had to rely on this one because this is CE marked, and this project was funded by the Ministry of Defence. And I'm not talking about the Indian Ministry of Defence, this was the UK Ministry of Defence, who like to throw the book on you when it comes to rules. So you've got to follow the rules, and they would withdraw funding if anything went against the rules. So we needed to have the research ethics approvals, and that's why I had to go through all that pain of testing on myself regularly. And we also needed to have use these commercially available ones, because I mentioned this project was about simultaneous monitoring of glucose and lactate. What that means is you should be able to use the same potentiostat in a multi-channel format and be able to measure glucose and lactate from the same device, but you could never get more than one channel running at a time. That is a big problem. So we ended up having 2 devices. That's why we needed this bag here, and you can see there's one potentiostat on this side, one potentiostat on this side, one sensor here, one sensor here. Poor me, you can imagine. But then the same thing happened to all the participants who followed this as well, right? And these studies were done over 24 hours. For those of you who want to know, somebody asked me about inflammation and stuff like that. When you remove it, this is my skin, I can tell you that for sure. When you remove it, this is the mark that it leaves, which kind of over after 12 hours, it kind of disappears, and in 24 hours, it's completely disappeared at all. I mean, these 2 are mine. I don't know, this looks somebody with bigger muscles than me, so it's somebody else, but clearly the marks disappear in 24 hours, right? So that's just, there was a question on tolerability this morning. So this is how you normally measure tolerability. You look at how quickly the marks disappear. Even I wouldn't like to, no matter, even if I'm a man who keeps his hands covered all the way till my wrist, still I wouldn't like to have marks on my body, because I like to go for a run, and quite often that requires running in t-shirts and vests. All right, looking at the data here. So this is some data that we've collected here. This is some data what we call as the chronoamperometric data, plotted as a typical biaxial plot. So on the left hand side is the current values that you're measuring. On the left hand side, on the right hand side is your glucose concentrations. These values are coming, the blue traces, the dots, blue traces is from the current values that we are measuring. The green dots, we also were doing capillary blood measurements. We didn't have access to a venous blood one, and as I said, this study was done more in a sports science lab rather than in a clinical setup. So when I was at Imperial, we had a fantastic clinical setup at Hammersmith, which was the clinical research unit at Hammersmith. You could easily do those studies. So the first studies that I showed you, wherein I showed you people sitting and resting and getting all the studies done, happily getting it done, that was because they were all doing it in steady state in a clinical research facility. These studies were done more, they were meant to be done in ambulatory conditions. So here the studies were done with people moving around. For example, I was teaching as well when I was doing measurements of glucose and lactate to see if my lactate levels increase because of any stress that I get from the students, and also looking at my glucose levels as well. If my glucose drops down too much, then I keep drinking. Normally I drink tea and coffee without sugar, so then I should probably start introducing some sugar in my tea and coffee. So on the left hand side is the current values. So the blue trace is showing you the current values over time. On the right hand side is your current values, is the glucose concentration values. The green is the capillary blood, and the lilac color that you see here is the trace from a CGM sensor, which was the Abbott sensor that we used here. So what we have here is one gold standard, which is your capillary blood here, one secondary standard, which is your lecture 3. So breathe. Thank you. That was really quick. Well done. So you have one gold standard or one primary standard and one secondary reference here, and then so you have something to compare against. As I said, we are measuring current values. You have to calibrate it to see exactly. And the funny thing here is, if you notice carefully, your capillary blood glucose values do not exactly current to the lilac ones, right? Although that's because the lilac current values here are designed to give you output values using ML, machine learning, and AI based on venous blood. And there's always a difference in the blood glucose concentration in venous blood and capillary blood. Therefore, you would never find them overlapping. But what we find is, you see these trends here. You see this is a postprandial peak. Postprandial peak is a peak that you normally get in response to a bolus. For example, you've eaten and you'll get a peak. If you have orange juice, instead of getting a broad peak, you will get a peak that will go up and come down, a very sharp peak. That's called a postprandial peak. And so we did these studies, and we did the studies for glucose on day 1, day 2, and day 3. What are we seeing here? The current values that you get on day 1 go down significantly on day 2 and day 3. Anybody? What does this mean?
Is it due to sensor fouling, or?
There's a lot of things going on there. Degradation of sensor. Anybody else? So would you call it degradation of sensor, or degradation of sensor performance, or degradation of or contamination of sensor? How would you want to define it? Everything together. Good. It's actually the right answer. There's a lot of things happening here, right? What are the sensors made up of? Going back to the last lecture. Enzymes. The enzymes degrade over days, right? There's another thing that's going on in the body. When you introduce any foreign body there's an autoimmune response, there's an immune response there. So what happens is how does the body respond? The body starts to produce protein capsules around the sensor surface. And when you create a capsule around the sensor surface, the amount of glucose that can diffuse to the sensor surface that goes down. And what do we know? We know that the current that we produce is directly proportional to the concentration of the glucose. Lower the amount of glucose that diffuses to the sensor surface, lower is the current. So there's something also going on here, which is biofouling effect, and this study has helped us establish that the biofouling effects actually start within the first 24 hours. So that day 2 there's a drop, day 3 there's a further drop here. Right? Now the reason these lilac curves don't look very different, I mean it's very, very light. These are the lilac curves that you have. The lilac curves, I mean those values don't look because they have actually accounted for that using their AI and machine learning tools, right? Because we are using the same software. We are not getting raw data from the CGM sensors. We are getting data from their software. So they are giving us process data. So their process data, blood gap, and the capillary blood glucose measurements are the same, look very similar, but in our case the electrochemical signals, they're dropping down drastically, which is normally indicated through these different color pyramid structures that you have shown in B here. Okay? So this is about the glucose sensors here. What about the lactate sensors? Lactate sensors are also showing you a similar trend. You can see that the lactate values, especially for the capillary measurements, is going up over time, and we are seeing a similar trend here wherein the lactate sensor measurement is going up through this lilac plot here. This is our sensor here. So when we plot the glucose sensors in this Clark grid error, you can see that 100% of our points are in zones A and B, although I would love to have 100% of points in zones A only. But here the green points are in zone A, the blue points are in zone B, which means there is still further scope to calibrate the sensors. The reading where you need to be very, very careful is this low value here, right? Does anybody know about the different zones between A, B, C, D and E? So zones A, as you move away from zones A towards zones D, it means that the effect of getting a false reading is much more harmful. So in zones A and zones B, if you're not along this straight line, if you're still in zone A and zone B, you can get away with it, right? And if you can look at it, you see the sensor, it gets wider at higher concentrations and narrower as you go towards this low concentration region. And that explains, we spoke about hypoglycemia. You don't want to be not predicting hypoglycemia because that can be really dangerous. So that's why when you're developing a sensor for glucose, you have to be very careful, and you have to have a sensor very, very sensitive in this region of 2 to 4 millimoles or below 65 milligrams per deciliter concentration. You can see here. That's why you can see it goes from wide towards narrow. That's how the whole zones are normally distributed there. And then zone B is moving parallel to A, and then zone C and zone D and zone E are quite outside. Anything outside this, if it's not an outlier, is totally unacceptable, because that can actually be can have a dangerous effect on the person who is being monitored. Yeah, so this also tells you a little bit about the flexibility. We also did a plot wherein we plotted our sensor performance against capillary blood and against so clearly if we are using a CGM sensor, we are getting much more values there. So you have much more. That's why this, if I rub this off and if I show you the number of points we have for here is definitely more than the points we have here. This is because here we are doing a comparison of the points we are getting from capillary blood values, right? You can't be taking a person and pricking him every 5 minutes, right? It's very painful, and I've done this on myself, so I can tell you that. There was a time when I was testing these sensors on myself, and I was using capillary blood as a primary reference, and I would get my boys to come and prick my finger, draw some blood, and do some measurements. I could tell you that, and I was trying to do as regular as possible every 10 minutes, and my fingers would go all blue by the end of the day. So it's a very painful thing. It's not an easy thing. So for this one we decided to do every half an hour. So but then the problem there is you get less amount of points. So you got to when you design your experiments on validating your devices, you got to be very careful. You have to think about every component, the pain element as well. I mean, you're getting somebody to volunteer in goodwill for science. You don't want to basically end up causing some. That's why you have to design your devices very, very carefully, because you don't want to kill somebody in the whole process of clinical studies. Although that will never happen. I'm just talking about an extreme case. It happens in in drug trials. I mean, there are cases where there have been extreme reactions to the extent that people have died as well. So this work was finally published in a journal called Lab on a Chip, which is a good journal, and the name also suits the kind of things. Just to show you a picture here, this whole thing is about 2 centimeters. You've got 4 different islands, working electrode 1, working electrode 2, which are diagonal to each other. We've tried to keep it equidistant from the reference electrode, so the distance between this and this is the same. So if you would have done this and this as the working electrodes, then I think there would have been a difference in the distance between the working electrode and the reference electrode here. And this is our counter electrode. Again, the thumb rule is it should be either the same size as the working electrode or bigger than the working electrode, ideally bigger than the working electrode, but that fact that it should be bigger than the working electrode was disclosed, we found that out later on by doing many failed experiments, and therefore we started having bigger counter electrodes, and you'll see, I'll show you the designs, the latest designs later on. Okay, and this was published in Lab on Chip. We published it as Lab on Skin, real-time metabolite monitoring with polyphenol based subdermal wearable patches. And then we also used hydrogels. So one of the problems with phenols is, although you get a nice layer of phenol, right, the problem, what is the problem with phenol there? Electropolymerization. Is it scalable? Is it scalable? If you are doing anything by electropolymerization, is it a scalable process? What do you think is a scalable process? Something that can be automated, something wherein you have a robotic arm and you dispense, rather than pipetting yourself. If you have a robotic arm and the robotic arm goes and dispenses, you leave it running overnight, come back in the morning, you have multiple of these ready. So we used hydrogels, which was basically PEG-DGE, polyethylene glycol diethyl glyceride. This PEG-DGE was really a good polymer, and we used these to show studies, and we did measurements over multiple days to show that the performance doesn't die down because it's much more thicker than this thing. Current values are lower than what we got with polyphenols, because polyphenols are much more thinner, but these are stable, and these can be made by scalable methods, which means that in the bigger picture, when you make your devices, you can have scalable devices and you can have low cost devices compared to electropolymerization. You will need a much more harder setup for electropolymerization there. And now let's have a look at the data that came out of the Ministry of Defense studies here. This was the participant study schedule. We were doing studies over 6 days. There were 3 days of pre-screening and 3 days of evaluation, and this is the program that our sports and exercise scientists came up with. They said on day 1 we are going to give them low GI meal, whatever that means. It basically means 36 grams of oats or sabudana or whatever you want to call it, or khichdi, and then get them to do some treadmill exercise. On day 2 we would give them high GI meal so that we can see much higher increased current, and then get the person to do some exercising, high intensity exercising, and then on day 3 again high intensity exercising with some high intensity cycling exercises for 30 minutes. This was the whole plan, which was designed and approved very well by the Ministry of Defense Research Ethics Committee, because you cannot do anything, especially if they're giving you the funding, you have to follow that. And it's going to be the same thing with you as well. Wherever your Research Ethics Committee is from, you will have to follow the protocol. You will have to get your protocol approved by them. Just to tell you a little bit about the translational studies. Here we again did some tolerability studies using visual assessment methods, right? Again, comparing microneedle with Freestyle Libra and fingerprinting here, finger pricks sampling here, and as you can see, people who are, would give you high scores for finger prick, that's here. Libra and microneedles seem to be nearly the same because we're using an applicator, and some people thought that it's much more easier. Microneedle, we were using moderate thumb pressures, and we were also trying to use applicators. People sometimes didn't like it. It's like, oh, this is too crude. While with the Freestyle Libra, the thought process is that it's something which is very, very hidden. You don't even realize, and it's just gone through. Although this one is subcutaneously implanted, and this one is something that is subdermally inserted. So there's a big difference there, but still, the Spain scores look to be, comparable. These are meant to be higher, but they are comparable here from this particular data that we see here. Again, looking at the tolerability, we also did a further classification of inflammation. So we had erythema for very severe conditions, edema, pruritus, and petechia. So we saw that normally people would have some level of inflammation there, and erythema was only seen in one person. Erythema is where the skin really goes red, very erythema, as the name suggests, is something red in color, and the inflammation is much more evident. But that was only one case that we saw here in the case of erythema. How we were using it in terms of looking at the performance, somebody mentioned about interference with sweat. Who was this person? There was a gentleman who raised, yeah, so interference with sweat. Here's your answer here. You can see the devices here. As you can see, there's also a thin film there which is covering the base of the devices there as well, so that you don't get any sweating when you push them into the skin. And these needles are only under your skin, so they will only measure what's under your skin and not what's over your skin there as well. Okay, so the idea was to have a silver chloride reference electrode, which is your this electrode is your silver chloride reference electrode. This is your counter electrode, and these yellow color thing, they're looking yellow because they are want a better answer. They're glucose sensors. Glucose oxidase is yellow in color. Why is glucose oxidase yellow in color? Yes, well done. You will get a treat for him. Flavin, glucose oxidase has got flavin, FAD, flavin adenosine dinucleotide, right? Well done. So that's what's good. Why is milk yellow in color? Milk has got a bit of yellowness, right? You can see the difference in milk, cow milk, goat milk, sheep milk, and of course, so there's no yellowness in soya milk. No, it's riboflavin, again flavin there. Okay, so these yellow color things are your glucose oxidase working electrodes there, just to show you a clear picture there. And as you can see, the sensor was inserted at the back of the arm, and the person is getting ready for all the measurements. We also had a mask there. We were measuring oxygen levels and carbon dioxide levels as well during the exercise process. Just to tell you a little bit more, palm sense, we had to use the palm sense Sensit bit, which is a portable potentiostat that's available there, and that's how it normally works. In an ideal case scenario, this is how your results should look like, wherein basically you have your red dots, which is your capillary interpolated blood, and your dotted lines, which is your microneedle, and they should have a nice overlap. You'll see most of the publications which have been reported like this, but what they fail to mention there here is that this would be something where the data has been processed either using machine learning, some smoothing algorithms, something that people of the likes of Professor Khalid Mirza know about how to smooth your data and play with your data to make some sense of your data, whether it's machine learning or AI thing as well. But we were lucky, only on one of the days we got data which looked like this. On the rest of the days, the data looked more like this. This is to give you some examples of the different participants, how the data looks like. I'll have to scoot through all of this because I think we still have time, but I don't want to bore you with all the stuff. Is it okay? So you can see here, this is day 1 studies. This is day 1, you break here. Day 2, you break here, and then this is day 3. So the measurements are only done during the daytime. Unfortunately, that was one of the requirements of the research ethics approvals. You cannot do any measurement after 5 p.m. and not anything before 8 a.m. because that's the only time when a doctor is available. So when you're doing clinical studies, you need to have a person on site, unless you're doing it with the clinicians and you're doing it in a clinical research facility where you have nurses who can, if you have an anaphylactic shock, they can administer something to you. If you don't have that, then you can only do the studies when you can contact a doctor on the phone, and the only time the doctors are contactable is 8 a.m. to 5 p.m. during the daytime. So therefore we had to break the studies, which was something that we didn't really like because we wanted continuous monitoring, as in continuous monitoring even during the night time. But look, I mean honestly, we're still getting to do a lot of studies there, but we were not taking the devices out. We were leaving the devices in there so that if there was any biofouling, let it affect the performance of our devices. Let's see what happens to with the biofouling. Let's see how much does it affect our performance. And that also helps all these data, if you gather all this data, do multiple studies, and this is then fodder for your machine learning and for your AI. You can build your AI tools around this particular thing. So this is participant studies done from 15th to 17th of January 2024, and this is again, this is the glucose oxidase sensor, this is the lactate oxidase sensors. Nice thing, you can see these postprandial peaks here, and these postprandial peaks are not there for no reason. These are postprandial peaks which are in response to a bolus. I keep on using the term bolus. When I say bolus, it means that there's been an event wherein a person has been consuming some food. Day 1, day 2, day 3, I mean different boluses there, and I mentioned to you about high GI meal, high energy meals and low energy meals. So day 1 is low, and then this gets higher, and then it gets higher, and that's how it was working here. And with the lactate as well, the exercise, you can see that more lactate is high intensity exercise is giving you more lactate production and things like that. And then something happened here, the sensor performance went down. So you have to do many of these kind of studies there. We did about 15 participants to get the final results there. That's day 1 data. This is just breaking down the data, what is happening near the exercise. You can see here the lactate level goes up, the lactate level goes up in terms of the current values as well. The current, so this is again a biaxial plot. This is the dots are showing you the lactate levels from the capillary blood measurements. The red traces are showing you the measurements from the sensors that the current values that are obtained from the sensors. And as you can see here, the lactate levels go up with the and you also see the capillary blood glucose values going up as well. So just to show you near the exercise what happens there as well. This is day 2 for the 3-hour studies. Day 3 and things like that started to happen. So what we did was we did all the studies and then we made a table. The problem we had is that, again, as somebody mentioned here, we started off with these kind of devices where the base was not covered, and then we ended up with these kind of devices where we had made these kind of like stencils, and we started using those stencils and we started sticking them onto the devices so that only the needle part, which is the exposed part, the base is all covered there. So we were using the green tape here, we were doing modifications here, green tape, black tape, trying to use different tapes to see which one is the best insulating tape and which is giving us good results. We also did some capacitance discharge, also increases the counter electrode area as well that I said to you, because this information came to our knowledge as well, and we did different types of things, and then we try to make sense of the data. But again, as I said, the problem here is, look at the data, it's not the best data, it's not very smooth, and I'm going to show you. And these are how you're getting the artifacts as well. You're having problems wherein suddenly the data has gone missing and you're getting the artifacts, you're getting unnecessary peaks. I mean, this is all smooth data, but if I show you the actual data, it's a lot of spikes there. This is all 5-minute averaging and things like that. That's what smooths it. But we really could not make a lot of sense with these kind of data sets that we were getting from the different participants. Participant 9. So we then did a summary here and look at our MARD values here. 54, 40, 55, 52. I think the best we had was 30 here. Okay, if you look in terms of capillary blood, we are doing much better here. Here the MARD values are 14 and 10. Right? These MARD values are comparable to the commercially available sensors. Commercially available sensors, when I started attending the conference, they all started from around 30, and they've all come down now to nearly 8, 8.5, 8.7, 9. I haven't seen anything which is below 5. Have you seen anything? No. So the MARD values, typical MARD values, when you compare the performance of your sensors to the commercially available ones or to the gold standards, are ranging between 8 to 12 is the MARD values. Here we were getting something here, but I think we used some compensation electrodes here. But again, the data doesn't make much sense here. This was also looking good here at 7.56. So the conclusions here is, when you're doing continuous monitoring, there are a lot of artifacts, and you need to use the data, you need to train your data to be able to address these artifacts. These artifacts can destroy your clinical studies, right? And I'm also here to tell you so that before you even start your clinical studies, you have everything set up nicely, and I'm able to share my experience with you so that you don't have to reinvent the wheel and do the same mistakes and go through the same painful journey to get the best results. Please use my experience here. I'll be more than happy to share all the publications that have come out of these translational studies. Use those and then see what gives you the best studies here. Okay, so artifacts are what normally contribute to the ambulatory data, and they are not fully understood. You have a lot of biofouling effects that was already established through the previous work. The biofouling will actually affect the sensor performance. We can eliminate some of the artifacts by using what we call as the counter electrodes, or we also call as compensation electrodes, or an auxiliary electrode, AME. And we need to do a lot of studies on these AMEs, and we also need to bring in tools like AI for better data analysis and interpretation. In the next part, I'm going to show what happens. So this is the research group that was involved in those studies here. I was very fortunate to have Arjun, my postdoc. So if anybody wanted to ask any questions on postdocs, I can tell you that. And I had a very international team here. I have 2 people from Japan here. I had a lady from Brazil, and I had 2 students from China and 1 of my PhD students who was from East, and this was my lab, how it looked when I was in Swansea University. I had this is where we were preparing the devices, working. That's Beth Norman, who isn't in this picture here, who worked in this particular project, and as I mentioned, this was funded by DSTL, and the initial project was funded by the NIHR. So this was all about how we did those studies under the restriction, because with DSTL projects the other problem you have is you have a timeline to follow. They will not allow you to go beyond a certain timeline. So that's very, very important. So we did everything as part of those DSTL studies, and then when the project finished, by the time the project finished, we had a student who was able to help us with the AI model here, right? And then what we did was we used the same sensors, same devices, and then we tested it. And this time we didn't start plotting our raw data directly. Whatever we had learned in our previous measurements, we used that to train our AI model, and we were using the raw current data and we were training our AI models. And then again, this is an example where you see simultaneous glucose and lactate monitoring, and the data here makes much more sense. We are not trying to emulate either capillary blood or the subcutaneous values. We will definitely get different values, but what we are trying to do is similar to the subcutaneous continuous glucose monitoring sensors, try to predict values which are much more representative of what's happening in your systemic circulation, what's happening in the venous blood. Okay, so here is, I also wanted to show you some of the tools that you need to do. So when you start working on wearable devices, especially with microneedles, the first question you ask yourself, are these microneedles actually sitting in the subdermal space, right? How do you find that out? You find that out using techniques such as optical coherence tomography. Do you have an OCT here? You have an OCT here. Perfect. So you are all well set, but for the OCT you need to have a substrate which is transparent, right? If it's something which is made up of stainless steel and things like that, you wouldn't be able to image through it. These are images that have been taken from Belfast University by Lalit Vora, and Lalit Vora has actually taken these nice images for us to show you. This is basically to showing you the skin layers. That's the conduit that you're normally creating, and this shiny bit that you see here is the stratum corneum layer, and the skin, as you can see, is nicely penetrating, creating a conduit around, and it's measuring in this interstitial, in the subdermal space here. This, as I said, this shiny layer is your stratum corneum, right? And it's nicely, if you measure the height of this one, it's going down about 1000 microns, or about nearly about 980 microns, or nearly 1 millimeter deep into the skin, which means that it's sitting in the subdermal space very nicely. So this was a proof that so you know, when you get different, and you have to make sure that your needles are not moving, because it's the outer surface of the needles that are giving you the current values. If you keep on changing the surface area, therefore you might have seen that in the images you see a pink kind of a band there, which is again used to secure the thing in place. Once we start using the AI model, we can make much more sense of our data. Just to kind of show you here, this is a good kind of thing. I wish I can zoom into this here. You can see there are 3 sets of data here. You have a lilac plot, which is the CGM data. You have the green plots, the dots, which is the capillary blood measurements, and then you have the blue plot, which is your measurements from the capillary blood glucose. Sorry, measurements from your subdermal wearable patches. All right, and as you can see here, they are nicely overlapping with the capillary blood, especially this part here, right? And then you can see that as the capillary blood goes up and down, your blue trace is also going up and down. You can make much more sense of your data here. You can see that you can record or you can monitor the events much more closely here. And similarly with the case of lactate as well, you can see that lactate is pretty stable here. Seems like a very good athlete here, because good athletes, because by their training, I mean, this is definitely not myself, so I can't say that my lactate stays the same, but then you can see here when you start doing rigorous exercises, high intensity exercises, the lactate levels are going up, which can be seen in the form of a trace, which can be seen in the form of this high VO2 and VCO2 values. So that's how we normally, that's our secondary reference there, and the same thing is seen when you do this exercise thing here as well. This was achieved through machine learning and AI. These tools will be discussed by Professor Khalid in one of the sessions, I think, and also Dr. Prasanna will also be talking about these. So now if you look at the performance evaluation, the performance looks much better. You have a lot more points. I mean, all the points are in zones A and B. This is comparison of CGM versus capillary. I deliberately put this here. CGM is a commercially available device. Capillary blood measurement using blood glucometer is a commercially available device. Clearly the outputs are going to be different, because one is predicting the value in venous blood, the other one is predicting the value in capillary blood. So clearly you wouldn't expect all the points to be along the straight line. Had it both been predicting the same values, or had the CGM sensors using software which predicts the value in capillary blood, everything would be along a straight line along in the middle, along this particular straight line here. Everything would be along this particular line here. But here you can see that you're getting some variation there, and that's what gives us the bit of margin there when we compare our subdermal patches versus CGM and our subdermal patches versus capillary blood. We can see that the points are all in zones A and zones B, right? And we don't expect, and if we show that all the points are in zone A, then we are making up the data. It's not going to be possible for us to show that they are the same. In terms of the lactate sensors, you normally, as I said, you have a bland Altman plot. The bland Altman plot tells you the correlation between the subdermal patches versus the measurements that were done with the capillary blood. You can see most of the points are along this straight line that you see here in the middle here, and these zones are zones of 95% acceptability, and everything is within that 95% acceptable zone. The differences, if there are any, are there. Having said all of that, you also have many outliers which are outside, which are clearly again artifacts that need to be addressed, which I'm going to leave up to you guys to pick up and address as part of your research here. Okay, I think that brings us to the last slide. So basically, to summarize, we have, as I said, we still have artifacts. I showed you the example of lactate sensors here, where you have the lactate sensors. The artifacts, they do still pose challenges in real-time continuous monitoring, and I think this is something which can be deeply explored with the help of machine learning and AI models, because we know there are examples. The classic example is that of Dexcom sensors that are commercially available, wherein they stopped working on the sensor side of things and they have started working more on the machine learning. Wherever there is a trend, you can bring in machine learning. If you know that you're using glucose oxidase, you're using lactate oxidase, there are new terms that have been introduced now. We call as factory calibration. Anybody heard of factory calibration? Sorry? You heard about factory calibration. So previous clinical studies, when they were being done, you would have the sensors being implanted, right? And a lot of those sensors were implanted. The Enlight sensors were implanted in the abdomen, right? And the way you would optimize, or the way you would calibrate those sensors, was you would optimize, you would implant that in your abdomen, and you would have a blood glucometer reading, right? So it would ask you at the end of the warm-up session, after 1 hour, the sensor would warm up and start, and it will say, what is your capillary blood glucose reading? It would take that reading, and it would take readings once every day. So clearly, that's how you would normally start to build up your machine learning models and AI models. We all know about this enzyme glucose oxidase. We all know about the lactate oxidase. Both of them have got their characteristic Km values, and we know that these Km values, or the apparent Km values, will degrade as the enzyme degrades over time. I mean, glucose oxidase, I keep on saying, is in a class of its own. You take glucose oxidase and throw it on the road, bring it back to the lab and make sensors out of it, you will see the sensors still working after 4 days of sitting in the sun. That's why I say glucose oxidase is in a class of its own. Lactate oxidase, unfortunately, is not very, very stable. I mean, now people have come up with direct electron transfer lactate oxidase enzymes, lactazymes, right? And those lactate oxidase enzymes are giving you good performance and stuff like that. But again, you need to bring in the machine learning and the AI tools, which can then allow you to use to kind of account for the loss in sensitivity, degradation of the enzyme, stability of the enzyme, and stuff like that. All those things can be monitored. And then the other thing is ambulation. When you're sitting there and doing a measurement, things are fine. Electrochemical signals, electrochemical sensors already have problems of drift, already have a lot of problem of baseline problems, baseline drift and things like that. Add to that another movement artifacts there, right? There's a movement artifacts, motion artifacts. Even if I'm sitting here getting a measurement done, I just lean backwards, there's going to be a spike, which is again a motion artifact, right? How do you get rid of these artifacts? These are things which I'm sure if we understand these, if there's a trend there, we can bring in the machine learning and AI and get rid of this. So the first part of the lecture was about, when I gave lecture 2, that was more about understanding the mechanism of how the sensors work, the biosensors work, and how do you put that to practice, and then on top of that, in practice, what are the problems that you have. That's what we've discussed in our lecture 3. I think that's probably my last slide, and with that I will be happy to open up the floor for any questions that you may have, and we've got plenty of time there, so please feel free to ask any questions that you may have.
Yeah, any questions? I know it's the end of the day, we are all tired. Yeah, Priyanka.
Sir, like you mentioned that there were very different participants that you performed this test on, and they had very like different monitoring of the microneedle sensors.
Yes.
So like, does it affect if the person is an average Indian is different from an average person in UK?
Absolutely.
So the ethnicity, how do you counteract these issues?
I mean, not only that, even there is also within Indians as well, you will have a lot of variation. You're absolutely right. There is interperson variability, and there's your sugar levels will also vary within yourself during the different events during the daytime. That's why we use what we call as primary and secondary references. We have, if you remember, those capillary blood values, because they are a good indicator of how your body is functioning, and they are a measure of your own glucose metabolism. So we use those primary and secondary references in each case, and then we compare that with reference to that, so that we can capture not just the variation between the different people, between the different participants, but also within the person at given durations, during exercise, before exercise, things like that.
So, but the standards are already much like, they have done all these research mostly in the Western side, right? So the standards are already according to them, because India is very like, they haven't performed all these kind of stuffs. So
there is actually, you'll be surprised, there's a lot of studies there, and the actual thing is, I mean, if you look at the way, if you compare the UK standards and the Indian standards, they are the same. So in terms of normal range, if you look at the range, 4 to 8 molar range, 65 to 110 milligrams per deciliter concentration, these are standard, these are international standards. So you don't have to worry about that. It's not as if that the studies are being done with a particular ethnicity or a particular race in mind. These are studies done for general human. And the funny thing is, when we do clinical studies in even places like UK, especially in London, we end up doing a lot of studies on participants from Asia. That's the reality. But we don't look at, we look at it more as human studies. We don't say Asian population and things like that. Yes, if we have to do clinical studies related to progression, disease progression, because that, as you said, genetic factors there. As Asians, we are genetically predisposed to diabetes, so the rate at which we metabolize things, those things are different. But those are more clinical trials. These are human studies here.
thank you.
You're welcome.
Yep. Any more questions?
I know it's a long day, but if you have any questions, please do ask.
Yeah, so it's more of a kind of case study. So in the previous lectures, you saw the technology, and then you saw the application of technology in this session through various trials. So I have a couple of questions you can ask. So I saw in your work, you are actually using this muscle on the
Don't
forearm.
say muscle. It's not intramuscular.
No, I mean this location on the
Yes.
forearm,
Yeah.
where you can actually press the microneedle to insert. So is there any reason of then why not? I guess most of the CGM sensors, they use the biceps.
No, so for
area.
the other studies, for the MOD studies, we were using the back of the arm.
Right, because I saw Joe Wang's group, they also had a Nature publication where actually they are using this forearm. I couldn't understand why.
This one is at the back of the arm, I
Right.
think. Just hope
So there is no specific reason why to choose the.
Look here, I mean, this is, you can see this is at the back of the arm.
Right, okay. So you could
this
choose.
is skin from back of the arm. This is not the forearm.
Okay.
This is the back of the arm.
So for the penetration force that is required, it's same whether it is fore or back. It
Yes.
doesn't matter.
As I said, with the exception of the backside and the
yeah.
feet,
Rest is
skin
fine.
is the thickness stays the same.
Okay, okay. So one more question, and this microneedle array, it's coated with platinum, right?
The bare structures are coated with platinum
So
and then functionalized with glucose oxidase.
right. So in terms of functionalization with GOX, how does it differ if the surface is from gold, whether it is gold or platinum, or the same process is same?
Platinum is a much better material when it comes to glucose oxidase,
Okay.
because it's got catalytic properties.
Okay.
Gold, on the other hand, gives you a very, very high background current,
Okay.
which means that low concentrations below 5 millimolar, you can easily miss that out, because if you do a comparison, get a baseline, gold will be much higher, platinum goes down quite fast.
Okay.
So the difference sometimes is nanoamps and microamps.
So okay, I guess, yeah, I see. So during the hands-on experimental session, we would be able to work on the PCB based.
Yes, we should be able to get a baseline.
And okay, and those are
Those are probably a mix of platinum and gold.
okay. Okay, I understand. Okay. Okay, good. We can have a look at that time also. Yeah. So during our experimental hands-on sessions, so you will see CGM sensors as well, commercial ones. We'll see the sensors developed by Sanjeev sir, and you all can handle it, use it to measure. You'll all have the opportunity to do that, and we also have potentiostats, so you can actually use the potentiostat, each one of you, and you can handle it so that you get a feel of this. So
Let's be very clear that these are more point of care sensors. They're not wearable devices,
yes,
because to be able to insert these wearable devices, we have to get the research ethics approvals.
Yes. No, we'll use it as a point
Yeah.
of care.
Yeah, we'll be using it as a point of
Yeah,
care.
not
Otherwise, you will only have 2 volunteers.
you and me. Okay. Yeah. So one more point that I think will be good to explain. So MARD, many people may not be familiar with this. So can you please elaborate on this MARD?
It's MARD values, mean arithmetic relative deviation.
Okay. Yeah.
So as I said, what you're basically doing is you're measuring the current, and then you're doing a calibration process. So you look at the highest value of your current, and you correlate that to the highest value of the glucose reading that you've obtained.
Yeah.
And then that's how you convert your current values into glucose readings. So now you have a row of values, and then when you compare your current values, the calibrated current values which have now been converted into glucose values, the output of that value or the predicted value to the gold standard, how much is the deviation there? How close are these values? The further they are, the higher is the MARD value. The closer they are, the lower is the MARD value. So MARD is basically mean arithmetic relative deviation. How much do they deviate from each other? How far are these values from each other? The same thing is seen here in the Clark grid error, where you have this line here. If the values were the same, all the points will fall on that red line there. But you have, in this particular case, you have a little bit of a margin here, a little bit of margin of error. You can have, instead of reading 3.6, 3.8, you can read 4. Slight difference there, but that's going to make a significant impact, because you're looking at the low glucose levels. But when you're looking at higher values, doesn't make a difference whether you're reading 10 or 11, right? So MARD values are much more significant when it comes to, it's normally used for looking at the performance of devices. You give your Clark grid errors and you talk about MARD values, but they actually tell you about how, the difference between the actual value, your predicted value or your output values versus the gold standards.
Okay. So it's percentage, I guess.
It's more like a percentage.
Yeah. So typical MARD values for CGM sensors is nowadays.
I would hold an average of 10.
Yeah, exactly. So around between.
There's actually a formula
8 to
for
10.
MARD values.
Yeah.
Which should be in the paper that I've given here.
Yeah. So we can actually also share sir's paper, so you can have a look also in much more detail. So I guess that's all from my side. Any questions audience have? No? So we can wrap up this session.
Yeah.
Thank you very much.
Great.
So
Thank
yeah.
you.